Alright guys, for this note we want to focus on exponential growth and exponential decay. Now we already know about exponential functions from before, so we know that an exponential function has the form y equals a times b to the x power. So we learned that in this function, a is the initial value and b is our pattern, either a multiply or divide pattern. But in these notes here, we're going to be more specific and look at it through exponential growth, when something is growing over time or increasing, and exponential decay, where something is decreasing over time. So let's start by first breaking down the parts of each of these models. For exponential growth, the a is still going to be the initial value. So if you think about it, it's still going to be the initial value. So that's your a term. It's your initial value in your story. Now in this case, this 1 plus r, notice how it's replaced the b. So this 1 plus r is still your pattern, but it's going to be called your growth factor. So this 1 plus r is going to be called your growth factor. It represents how much your function is growing by. Now in exponential growth, this will always be more than 1. It's 1 plus some percentage. So to identify by what percent it's growing by, we know it's going to grow. The actual r, so the r specifically, is going to be your percent growth. So it represents by what percent your function is growing by. And then last in this form model is going to be the t. Now the t is going to represent the time in the story. So I know I'm being a little messy here, but there's a couple of parts to this. So the t is going to be the time in the story. So this represents the different components of an exponential growth model. Now that might seem complicated just with the different arrows, but if we look at some examples, what does this look like? So if I look at this example here, notice how I do have an exponential function because the variable here is the exponent. And I can still recognize here from before a and then b. So think of before the a and b where a is the initial value and b is the pattern. So here I know I have a times 1.17 pattern. But in terms of the actual growth model, here's what it looks like. The initial value here is going to be 3. So the initial value is going to be 3 in this example. Now, as far as the growth factor, I'm going to put GF because of space, is going to be 1.17. So that's my pattern here, so it's 1.17. But to actually understand, guys, by what percent is my function growing, that's going to be this 0.17. So the growth factor is 1.17, but the percent growth is how much above $1. Again, think about money. How much above $1 am I in this value? Do you see I'm 17 cents more than $1? So in this case, I'm going to have a 17-cent growth, which is a 17% growth in this example. So that's how I can identify by what percent it's growing. So with that, let's look at example K. So again, in this example K, I have y equals 3 times 1.02 to the t. So I know it's exponential because the exponent's a variable. So in this case, my initial value is going to be 3 again. So my initial value is going to be 3. So I can identify that from the equation. My growth factor here, remember, whenever this is more than 1, it's going to be growing. So my growth factor here is going to be 1.02. So it's 1.02. That means I have a 1.02 times pattern. But to find the actual percent by which it's growing, just think about how much more is this value above $1. So it's like saying 1.02 is like saying 1 plus 0.02. So this 0.02 is the percent growth I'm going to have. And 0.02 is like 2 pennies, which means it's a 2% growth in this example.